Good morning, everybody. I hope you guys are having a good start to your Friday. This is Friday, November 22nd. Um, I'm about 80% sure that I am wearing the exact same hooded sweatshirt that I wore on Monday and on Wednesday of this week. Um, which is really just a fantastic, I don't know if I would say it's a coincidence, but it's really a revelation of I did a pretty good job of laundry this week, so that is something that I'm proud of. Um, so yeah, I washed it between Monday and Wednesday, not between Wednesday and Friday, because you don't need to wash everything all the time. It's just excessive. With that, we most recently have been talking about lipids, and we're going to continue that journey and continue that conversation. And we're leading up to a discussion of membranes. I think that we'll tap into membranes a little bit today. Um, and then on Monday, I'm going to give you guys a pre-recorded lecture, which will, excuse me, tap into membranes and metabolism, and transport across membranes. Now, with that as kind of a statement of where we are, I'm going to go ahead and, oh, not that one. Go to presentation mode and start our presentation. There we go. And I've got my chat open, so if anyone has anything to say or ask or anything like that, send me a message and I'll see it on this screen right here. Okay, so lipids. If you remember when we talked about lipids and introduced lipids, these are molecules that are soluble in organic solvents. And they perform a number of different functions, one of which is they provide a huge amount of energy, and they're long-term energy stores. There's a couple of different classifications. Fatty acids, which are kind of your, if you wanted to equate them to something, they're kind of your monomeric units. Triacylglycerols are the closest that you're going to get to I guess, polymerized lipid. But lipids don't polymerize like a protein or a sugar or, say, a nucleic acid does. And then you got glycerophospholipids, sphingolipids, and steroids. We are going to tap into glycerophospholipids, sphingolipids, and steroids a little bit today. More time than not will be spent again on fatty acids and triacylglycerols. So here's our fatty acids. These are three different fatty acids: stearic, oleic, linoleic, and alpha-linolenic acid. Now, these fatty acids differ in that they are either saturated, which is the one on the far left, and as long as I have talked about, learned about, or taught fatty acids, every time that I say saturated, I say it's saturated with hydrogens. So that is my kind of reminder that there's no double bonds in the side chain of a fatty acid, or in a saturated fatty acid. Then we've got oleic acid, which is a unsaturated, specifically a monounsaturated fatty acid. Linoleic and alpha-linolenic acid are considered polyunsaturated fatty acids, or PUFAs is sometimes the acronym that you'll see. Now, these are long chains, typically between, or in animals and plants, they're between 16 and 18 carbons long. And the notation that we use is 18:0, 18 being the number of carbons, and then the 0 being the number of double bonds, the 2 being also the number of double bonds. So 18:2 would be an appropriate representation for linoleic acid, and 18:0 would be for stearic acid. Now, your naturally occurring fatty acids are going to be in the cis configuration, and typically that first double bond in a mono or polyunsaturated fatty acid is found between carbons number 9 and 10. Now, that number right there, 9, is in reference to kind of your organic chemistry numbering. And so that would mean that your highest priority group gets the designation of 1. And in this case, a carboxylic acid is your highest priority group. Polyunsaturated fatty acids, you're going to have a pattern of double, single, single, double, single, single, double. and so on, depending on the number of double bonds. If there's at least two double bonds, the naturally occurring fatty acid is going to have a pattern of double bond, followed by a single, single, and a double. And if anyone is confused about that kind of terminology, let me know. Okay, so I what I got into the other day was this notation. Now, one thing that I want you to notice about these three different fatty acids is whenever we use this notation known as the delta notation, this right here, linoleic acid, for example, I'm going to highlight that one in red, and then I'm going to switch colors for alpha linolenic acid. For linoleic acid, we indicate with a delta symbol where the double bonds are. And we specify where all of the relevant double bonds are. So we would say delta 9, delta 12, because our double bonds are found at carbons number 9 and 12. They begin at 9 and 12 respectively. Now, that can be a little bit confusing because it's like, wait a minute, it's between 9 and 10. Yes, but we use the number where it starts. Or let me rephrase that. We use the lowest of the numbers. We don't have to say it's between 9 and 10. We can just say it's at 9. And that implies that it goes from carbon number 9 to 10. That's our delta notation. Now, our omega notation is a little bit different. The omega notation it's kind of like I would say that it's almost like a gatekeeper. And what I mean by that is it has a little bit of a barrier, and you have to bring some outside knowledge. Um, your delta or your omega notation, I'm sorry, is also indicated as the N notation. So here what we have is 18:1 delta 9, and then 18:1 N minus 9. In this case, for the N or the omega notation, we are starting at our methyl carbon, and then we are counting up. And so I this is a good example or I think that this is a good example because it can be confusing. Because if you just look at oleic acid, well, the double bond is at 9, whether you're using the delta or the omega notation. Because if you start from 18 and subtract 9, you're going to end up here. Or if you're using the delta notation and you count up from here, this is going to be 9. So it's a little bit confusing, or it can be confusing. Now, if you look at linoleic acid by contrast, well, linoleic acid is denoted as delta 9, delta 12. Okay. And that notation, we are starting from our carboxyl group. Omega, or N minus 6, by comparison. Well, then what we're going to do is we're going to count up from our methyl carbon. That's carbon 1 in the omega or N notation. 1, 2, 3, 4, 5, 6. So that's where our first double bond is. Now, the part where I said, well, you have to bring in some outside knowledge or background knowledge is in order to place, let me erase all of these, in order to kind of properly draw or properly identify or model an omega minus 6 or an omega 6 fatty acid, you have to know the pattern of double bonds in naturally occurring fatty acids. You have to know that your double bond pattern is double, followed by a single, followed by a single, followed by a double. You have to know that it's double, single, single, double. So the omega scheme or the omega system is, well, find your methyl group and count however many in that is, or however many carbons in your number is indicating. So minus 6 or omega 6 fatty acids have their first double bond right here. 6 from the methyl group. Okay. Now, where are all my drawings? That can be confusing Um, but I think that the most important thing is that you understand that the N or omega, N and omega are interchangeable. Delta is a different numbering scheme. Now, with that in mind, I think a very reasonable and good question is why? Why do we have two different numbering schemes? And the reasoning is largely because of different backgrounds and disciplines. The delta numbering scheme is more relevant to chemists, whereas the omega numbering scheme is more relevant to like physiologists or nutritionists, not nutritionists, dietitians. So it has like a nutritional component, which is why, if you eat salmon or take an omega-3 fatty acid supplement, well, in terms of numbering that carbon, that would be your carbon number one, your methyl carbon, two, and then three. That is an omega-3 fatty acid. So when you're thinking about that, and we jump back, this fatty acid, alpha linolenic acid, is an omega-3 fatty acid because we're starting at one, two, three. Okay. So those are our two designations, omega and delta. Those are our big, um, I guess, nomenclature schemes when it comes to fatty acids. All right. So now, first top hat question. And we got 30 seconds on this one. The delta fatty acid numbering scheme starts from the blank end. Carboxyl, methyl, neither of these are right, or the fluorine. Okay, we got about 5 seconds left. Let's check out our answers on that. Stop. Done. Okay. Correct. Great. Carboxyl. So about three-quarters of us got this right. I'm happy that nobody selected fluorine. I'm happy nobody selected neither of these are right. For those of you who selected the methyl end, I think you just got mixed up on and maybe anticipated, well, omega. So the omega scheme is what starts at our methyl end. So let me write that out. This is, actually, I'll just use the symbol omega, and then I'll write the word omega. So, okay, there we go. Okay, good job. Now, next up with fatty acids, we're interested, in addition to what they look like and how they're identified, how they kind of function together. And I always like to think about this because this component of what we're about to talk about kind of has like a nutritional component to it. So fatty acid chains, what they are, those hydrocarbon chains, they're very non-polar. So they really like to be next to one another in an aqueous environment. And so what they're going to do is they're going to aggregate together because hydrophobic groups, hydrophobic molecules in an aqueous solution, they're going to cluster together. And they're going to form more complex and larger, higher order structures like membranes. Now, here what we see is basically a saturated fatty acid on the left represented by A, and then an unsaturated, a monounsaturated fatty acid represented in B. Now, tell me, just add to the chat how you would describe B, not A, but B, sorry, B. How would you describe that shape, kind of in comparison to A? Curved. Great. I like it. Now, bent, awesome. Those are both perfect. And those were both kind of the words that I was looking for. Um, Now, when you think about that, and you think about, I'm trying to think of a good analogy, but let's imagine that you've got 5,000 of those saturated fatty acids, totally saturated fatty acids. You think you could, I always kind of think about almost like, does anyone know what a pipe cleaner is? When you're a kid, you make crafts with pipe cleaners. They're the metal things with kind of fuzzies on the outside. Well, imagine that imagine that our saturated fatty acids are like straight pipe cleaners. You could probably cluster those together pretty tight. You get a handful and you cluster them together because they all have basically the exact same shape. And so if you think about those saturated fatty acids and you think about those pipe cleaners, they're clustered really close together and they can basically make something that's a really dense packaging of them. Now imagine if you have a mixture of pipe cleaners that are straight and pipe cleaners that have kind of a bend to them, like this, representing our unsaturated fatty acids. And let's imagine that those pipe cleaners that are bent, they're not going to kind of bend back to a straight form. And you try to cluster those together. Well, those bent pipe cleaners, those unsaturated fatty acids, they're going to kind of have a kink to them and they're going to have a bend and they're going to, think about, are they going to occupy the exact same space as a saturated fatty acid? Not really. No, they should occupy more. Absolutely. And you're absolutely right. And that's what we see at a molecular level, at an atomic level almost. Unsaturated fatty acids. Sorry, I have some coffee grounds that keep showing up in my mouth. Oh, good, I am recording. So unsaturated fatty acid chains, they have bends and they pack without as much efficiency as their saturated fatty acids. Okay. Now, this next figure down here is one that I always like to think about whenever I'm eating like I don't eat steak very much. But whenever I'm eating something that has lots of saturated fatty acids, you know, I always like to kind of imagine, let's say that so here's our saturated fatty acids on the left, and then our unsaturated and saturated mixture on the right. And here, those red boxes indicate where the double bonds are. I always like to imagine, a 3D, like a little cube. And okay, I'll do it. We've got time. Um, I'm, I fancy myself an artist. So like, look at this. Boom. Look at that. That's a cube right there. Okay, so let's imagine that we get a bunch of saturated fatty acids and pack them into that cube. You're going to be able to have a ton of saturated fatty acids pack into that small space. Because we're talking about this in 3 dimensions, and they're going to cluster together. Meanwhile, if we were to pack unsaturated fatty acids and a mixture of saturated and unsaturated fatty acids, which one of them in this little cube O fats, where are there going to be more? In the cube that is has saturated fatty acids exclusively, or the mixture? Which one of them will have more fatty acid molecules packed in there? Perfect. You're absolutely right. So anytime I hear or think about saturated versus unsaturated fatty acids and, consumption of them, like dietary sources of saturated or unsaturated fatty acids. Well, it doesn't really have to do with one is good, one is intrinsically good, and the other is intrinsically bad. Instead, the question of the saturated or unsaturated fatty acids is, well, if each one of them provides X many calories and you eat saturated fatty acids exclusively, you're getting more calories from this little cube of fats if it's just saturated fatty acids compared to if it's a mixture of saturated and unsaturated fatty acids. So if you think about like this little cube of fats, if it's saturated, more calories than if it's unsaturated. It's not to say that like, I always like to think about this in the context of kind of a dietary component and consumption. And it makes me think about, the advice of, oh, you should never eat the yolks with your egg or something like that, because that's got a bunch of saturated fatty acids. Well, that's not inherently a problem. The question is, um, like, do you need that fuel source? Do you need that energy? People who do like I don't know, like high intensity training, and they go out and they run 12 miles and then they ride their bike 60 miles every day. They probably need more calories and need more caloric intake than someone who rides their bike 3 miles and runs 2 miles in a day, because there's just more energy expended there. Okay. Now, in terms of what these molecules or how they differ from one another on a physical property level, we've got at the top of this, we've got nothing but saturated fatty acids. Now, what I want to draw your attention to is all of these fatty acids that I've highlighted, they range from 12 to 24 carbons. They have specific systemic names and common names. I don't want you to worry about or know those common names. There are some fatty acids that are a little bit more common that you might encounter, specifically palmitic acid. Palmitic acid is 16 carbons and stearic acid is 18 carbons. Those are kind of more biologically relevant to people. Now, those fatty acids have a melting point of 63 and 69.6 degrees Celsius. So what that means is that, well, they're a solid at room temperature. But if you heat them up to 63 or 69 degrees Celsius, that's when they're going to begin melting. Okay. So what is a trend that you notice looking at this table with melting point and number of carbons? How does melting point change as the number of carbons changes? Does it change? Perfect. Wonderful. Wonderful, Morgan. So as our number of carbons increases, so when we go from 12 to 24, our melting point went from 44 to 86. Okay, so that's not completely linear, but it's a pretty steep increase. Okay, then when we get down to the bottom half of this table, the bottom half of this table is displaying our, well, unsaturated fatty acids. We've got fatty acids that are 16 all the way up to 20 carbons. Now, the first two fatty acids, 16:1 and 18:1, are monounsaturated fatty acids, and they have melting points of 1 and 13 degrees Celsius. So that 1 to 0.5, that is the melting point. So 1 degree Celsius, in a range from 1 to 0.5 degrees Celsius, cis 9 hexadecanoic acid, also known as palmitoleic acid, a 16 carbon long monounsaturated fatty acid, is going to be, is that a liquid or a solid at room temperature? If we say room temperature is about 23 degrees Celsius. You're absolutely right, Morgan. It is a liquid at room temperature. Okay. What about oleic acid, also known as octadecanoic or decanoic acid? Liquid or solid? Again, absolutely. Great job, guys. Okay. Now, when we look at just those two, does our trend with that we looked at earlier, the number of carbons as it increases, the melting point increases? Yeah, that remains true. We see that when we increase the number of carbons from 16 to 18, our melting point goes from 1 to 13. Okay, so that's consistent. Now, when we added that that double bond there. What happened to our melting point by comparison to these right here? Oh man, it fell off a cliff. It plummeted. Absolutely. Okay. Done, 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 done. You're absolutely right. And the degree of saturation, so the number of double bonds, as that increases, what happens to our melting point? Okay. Thank you guys very much. You're absolutely right. So I'm going to go ahead and clear my drawings because I'm so happy to say you got it. So there is kind of a trend. As the number of carbons increases, the melting temperature increases. As the number of double bonds increases, the melting temperature decreases. Now, you do kind of split hairs a little bit, but the number of double bonds is going to take precedent and impact the melting point more. So we'll proceed from there. Good job. Okay. Now, question here. Which fatty acid has the lowest melting point? We got 45 seconds on this question. All right, we're just about done. Let's check our correct answer. Okay. We got about more than half who said that it was 18:4, and you guys are correct. So I gave you A and C as kind of opposite ends of the spectrum. So our lowest melting point, I think that maybe that's something that I have a tendency personally where I'll think about melting point and I'll be like, oh, okay, okay. Um, I have to put that into context sometimes. And so what I'm looking for is something that, I mean, if we looked back at the previous slide, that would give us some insight. But what we're looking for with the lowest melting point is the molecule that has the most double bonds. And so colon 4 indicates that we've got 4 double bonds, so that is going to be our lowest melting point. 18:0, that's going to be the highest melting point. So another way of phrasing that is going to be the solid for longer, imagining that we're increasing the temperature on a mixture. So that's going to be a solid up until a higher temperature. 18:4, let's just imagine, let's put it into context. At room temperature, that's going to be a liquid. 18:3, probably a liquid at room temperature. 18:0, probably not a liquid at room temperature. So I think that it might be helpful, and you'll probably see questions on your exam that ask about something. Is this a liquid or a solid at room temperature? Now, with that in mind, in terms of context for the previous slide, I'm not expecting you to remember any of those specific values, but the liquid solid questions would end up something like 18:2 and 18:1. Which one of these is more likely to be a liquid at room temperature? In which case, you might not know either of their melting points, but you'd want to pick the one with the greater number of double bonds. The 18 colon, I think I said 2 or 3. So 18:3. Okay, so now we're on to triacylglycerols, also known as triglycerides. These are if you get an annual physical, part of your blood workup is to do a lipid panel and to look at your or not your soluble, but your free fatty acids and to look at your triacylglycerol levels. So triacylglycerols are triesters of glycerol. So you've got your glycerol backbone, and to that, you have an esterification where you take the carboxylic acid of a fatty acid and you make a ester on this glycerol backbone. Okay, so shown here is a triacylglycerol. Now, those triacylglycerols can vary a little bit in terms of the length of the fatty acid chains, but think about a triacylglycerol as having 3 times the energy as a free fatty acid because it's carrying 3 fatty acids. Most common, or most of them are going to contain 2 or 3 different types of fatty acid residues, and types being lengths as well as saturated or unsaturated. Now, melting temperature for fatty or for fats. Okay, so think about this in terms of maybe something that you're a little bit familiar with. So we've got olive oil. Let me actually change that. Let's highlight just olive oil. We've got olive oil, butter, and beef fat. Now, the question is, if you throw a steak on your grill, before you throw it on the grill, is there fat that you can actually see? There absolutely is. If you go to your kitchen and provided that your air conditioning is functioning and everything's good there, you're going to find a stick of butter if you keep your butter out in a butter tray. And it's going to be kind of a soft solid. Olive oil, by contrast, is going to be a liquid, more than likely at room temperature. And so here's our naturally occurring fats and the states that they're in. In addition to that, what this slide is showing is the composition of them. So here what we have with olive oil, which is a liquid at room temperature. Um, this is going to be a we have a very high percentage of unsaturated fatty acids, whereas butter here, we have pretty much an even composition of saturated and unsaturated fatty acids. And then beef fat, we have a higher concentration of our saturated fatty acids that are a little bit longer. So if there's one thing about this slide that you want to kind of like hone in on, what you could do is just say, all right, well, I'm looking at the C16, 18 saturated fatty acids. What do I see? Well, beef fat, butter, and olive oil. The beef fat, that amount is going to have the highest concentration of our saturated fatty acids. Butter is going to have the lowest concentration of fatty acids, or sorry, a lower concentration. And then olive oil is going to have the absolute lowest concentration of those saturated 16 to 18 carbon fatty acids. Now, okay, let's go on from there. I want to talk a little bit about the biological role of triglycerides and triacylglycerols, and then I'm going to jump ahead a little bit because I want to talk about one thing that's very relevant for membranes. So, your biological role of triacylglycerols, they're energy reservoirs. The fat content of normal humans allow them to survive for 2 to 3 months. But if you remember that example that we talked about the other day, Mr. Barbieri for better part of a year, um, then triacylglycerols also function to conserve heat and help you internalize and keep heat. They function to insulate. Now, with that said, I was born in 1983, and right around, I was like 1995, 96, Frito-Lay and a bunch of other companies, what they did was they were trying to come up with a fat substitute because they loved selling Doritos, but people didn't like eating so many Doritos. Just as an example, I really mean potato chips in general. Um, and so they made this molecule that was called Olestra. Now, Olestra structurally, it's kind of interesting. Um, what it was basically a six-membered ring. There we go. And you know how on your sugars, what do we have at basically each one of our carbons on a sugar? Got a nice little OH group. Okay. Now, if we run back and look at our triglycerols and our glycerol, we formed an esterification, or we esterified. We added these fatty acids to glycerol. Where did we add them? We added them where we had an OH group. Okay. So basically, where you see an OH group, that's potentially a place that you could add, well, an ester or sorry, a fatty acid. I mean, there's other modifications that you can make, but people at researchers at Frito-Lay were like, we found this molecule. We can take like a sugar, glucose, for example, and we got a bunch of hydroxide groups on there. What if we threw a bunch of fats on there, threw a bunch of fatty acids on there? The question was, if you put a bunch of fatty acids on there, kind of what would it look like? It would look like this. I'm just going to make it shorthand like that. Um, and so, question is, if you did that, what would your body do? Your body's going to see this thing and it's going to be like, well, I don't know what to do with that. That's strange. I've never seen anything like that. I see the fats on here, but I don't really know what to do with it. And from Frito-Lay's perspective, this compound, this molecule with a bunch of fats on it was great. The reason being is that fats provide like structure or some level of structure to things like potato chips. Now, your body sees olestra, that compound right there. I've only drawn one fatty acid, but just imagine that it's got six on there, or five or six. Your body sees that olestra and says, I don't know what to do with that. But in terms of like when you're chewing it, it's still got that kind of savoriness because there's still fats there. Now, what your body does is it can't metabolize it. Now, Olestra was a fat substitute in the 90s and maybe into the early 2000s, and they were packaged and labeled as Wow brand potato chips. Wow was a subsidiary or, just like another market or name. Um, because they were like they tasted just like Doritos or free or Lay's or whatever your chip of choice is, but they didn't have the fat content. And this was like a big thing. People were super pumped about it. Oh, this is great. I can maintain a low fat diet and eat all of these Doritos. And it was working like working like a champ. But then people ran into problems because it really caused a lot of gastric distress. And they would have very, very violent experiences as your body was like, I don't know what to do with this. I'm getting rid of it. And I think that there was I don't know that anyone died. Um, so, the person at the marketing meeting for Frito-Lay was like, but did anyone die? The answer I think was no. I could be wrong. I hope that I'm right that nobody died. Um, but I think that people got hospitalized because of like violent diarrhea. So it was bad. But Olestra is kind of this, it's almost like a Frankensteining of a biological molecule. Now, your more conventional fats, triacylglycerols, um, I presume that people who are in here know who Brad Pitt is. Um, if I mention fat and I mention Brad Pitt and I mention movies, is there a movie that comes to mind or a book that comes to mind when I mention fat and Brad Pitt? And I'm not talking about body fat, but is there a movie that comes to mind? And I'll give you a little bit of hint, a hint. Um, this movie has rules in it. And the first and second rule of this movie, or the activity in the movie, well, you can't talk about it. Absolutely. Fight Club. So, Fight Club, in that movie and in that book, one of the things that was done, or one of the like storylines in that movie, was that I guess the people in the Fight Club, what they would do is they would take fat, and I think that it was specifically from like liposuctions. They would get fats, and the type of fats they were getting were triacylglycerols. And those triacylglycerols, they would render and go through a process known as saponification. And from that, they would make sodium salts of a fatty acid, also known as soap. Now, this is kind of an industrial process. And I bring this up because um, it's a formative process because if anyone's ever been to Cincinnati, Ohio, one of the biggest companies in Cincinnati and the greater, I guess that would be the southwest region of Ohio, is a company by the name of Procter and Gamble. And Procter and Gamble is one of the biggest corporations in the world. They do everything. Um, you wear jeans, they probably made them. You wash your jeans, you're probably using a detergent from them. And Procter and Gamble really got started because what they would do is they rendered pig fat to make soaps. And so that was kind of where they started. So that is the industrial process, and I'm just going to label this P and G. I have a friend who works there, and he's yeah, that's the thing there. Everyone in like southwestern Ohio works at Procter and Gamble. Now, what your body does is it's going to take triacylglycerols and it's going to go through a process known as enzymatic hydrolysis, and it's going to use enzymes known as lipases. Lipases are a class of enzymes that will break fatty acids, or sorry, triacylglycerols down, and it will release a glycerol as well as your free fatty acids. So these free fatty acids that get kind of released separately, um, that is through the process known as enzymatic hydrolysis. Now, what I want to do here is I want to clear my drawings. I want to exit out of this. And instead, now I want to talk about um, membranes for just a second. Okay, so with respect to membranes, I want to get into membranes because what we've been talking about a little bit is we've been talking about physical properties of fatty acids. Now, I'm going to cover all the remaining stuff in Monday's lecture, but a membrane, typically when we talk about a membrane, we're talking about a lipid bilayer. Now, is a lipid bilayer the only form that a membrane can take? Nope, not at all. Now, what I want you to notice is kind of the function of a membrane. They can serve as barriers to toxic molecules. They can help keep, essentially, they can keep the stuff inside in and the stuff outside out. They serve as a nice barrier. Now, the major ways that a membrane exists is as a micelle, a bilayer, or a liposome. Now, what I want you to notice about these different membranes is that if a liposome is basically like a bilayer, but a more compact one. And notice that it has an aqueous cavity. So that has a polar region or a polar space in the center of it. How do you think that you would describe the internal parts of a micelle here using that same sort of terminology? To rephrase that, would you describe or would you think that the interior of a micelle is going to be polar or non-polar? Absolutely. It's non-polar because what we're seeing in the interior of the micelle is those hydrocarbon chains. So sorry I didn't make that, or I don't think that I made that clear enough, but um, basically what we've got is here are leg-looking things. Those are our non-polar chains or our hydrophobic chains. Those hydrophobic chains are, well, they're going to produce a very non-polar interior. Now, what that means when you look at a bilayer, the region, kind of the internal part of a bilayer where my arrow is pointing, that's also going to be nonpolar. So if something is polar and it's approaching a bilayer, yeah, it might interact with the polar head groups, but it's not really going to be able to insert itself completely because of the composition of that bilayer being very nonpolar. Now, what I want to do is really want to get to this slide right here. Now, this I think is I like to bring this up, and I'm happy that I'm getting it to it today because of the fact that, well, there's a temperature dependence on kind of the rigidity of a cell membrane. Okay. Now, this is a table from a study where E. coli, Escherichia coli, I just like to say Escherichia sometimes, was grown at different temperatures. It's grown at 10 degrees Celsius, so a little bit chilly, maybe in the 50s or 60s Fahrenheit. and then at 40 degrees Celsius, a little bit over 100 degrees Fahrenheit. So mild, and I would say borderline hot. Now, the ideal growth conditions for E. coli is about 37 degrees. Now, if the 37 degrees is the ideal growth temperature, will E. coli grow at these other temperatures? Will it grow at 10 or will it grow at 40? Yeah, it will grow. They will grow. Not too much of an issue. But the question is, what's going to differ? One thing that's going to differ is they're going to grow much slower growth at 10 degrees. And at 40 degrees, the rate might speed up a little bit, but viability might go down a little bit. And likewise, at 10 degrees, the overall cell growth and viability might also go down. So I'm going to say viability might go down a little bit. That's it. Yeah. Okay. Now, what I want you to notice and where I want your head to be is I want you to be thinking about the rigidity of saturated fatty acids and the kind of flexibility of your unsaturated fatty acids, whether they're poly or mono unsaturated fatty acids. Now, what I want you to notice here is that at a lower temperature, so at 10 degrees Celsius, looking at these four items, at 10 degrees Celsius, what do we have a greater concentration of? And I'm going to give you a little bit of direction on this and highlight these separate from these. At 10 degrees Celsius, do we have more saturated or unsaturated fatty acids? Unsaturated is absolutely, Morgan. Okay, so let's think about this. If we think about our melting temperature or the typical melting temperature of a saturated fatty acid, or our melting point is kind of high for these. So you could kind of think that they're going to be a little bit more rigid, more solid at a lower temperature. So I'm going to say more solid at a low temp. Now, if you think back and you're trying to, I don't want you to think about those melting temperatures and say, oh, well, the melting point here has got to be like 70 degrees. Well, that's a little bit of a not 100% because of the fact that, a membrane is a mixture of things. And so we're looking at percentages. Okay. So then for our unsaturated fatty acids, our melting point is low or lower. And there it's more liquidy at a lower temperature. And we have a higher concentration of those unsaturated fatty acids at a lower temperature. Between 10 degrees and 40 degrees Celsius, what do we want that membrane to look like? We want that membrane, whether it's at 10 degrees or 40 degrees, to have the same mobility, to have the same motion, to have the same flexibility. Whether it's 10 or 40 degrees, that membrane kind of has to have the same mobility and flexibility. And in order to achieve that, E. coli are going to produce and pack into their membranes a higher concentration of unsaturated fatty acids than saturated fatty acids. Meanwhile, at a higher temperature, well, again, we still want the membrane to be moving like this. So how do we achieve that? Well, we achieve that by reducing the number of unsaturated fatty acids and bumping up the concentration of our saturated fatty acids, which is what we see right here. So your takeaway from this is at a low temperature, the cell is going to produce more and more of your unsaturated fatty acids. Whereas at a higher temperature, we want to produce a greater concentration of saturated fatty acids. Saturated fatty acids are rigid. Do we need them in a membrane? Well, if the temperature is high, yes, we do. Because we want that membrane, whether it's at 10 degrees or 40 degrees, to have the same kind of fluidity and same sort of motion. Now, that's where I'm going to stop. I'm going to say that your quizzes that are on Canvas that are due on Sunday, I would go ahead and, look over the PowerPoints because there are some questions on the third quiz, or I think it's like 18 or something like that. Um, and that is going to be, let me see how to phrase this. Those are going to be some questions from the previous slide talking about lipids. So kind of have that open. You're welcome to have that open because all your quizzes are open note. So you've got 3 quizzes due at 11 p.m. on Sunday. And I've got a question in the chat that I'm going to respond to in just a moment. But in the meantime, I'm going to go ahead and say, I hope you have a wonderful weekend. I hope you have a great break. Monday is going to be pre-recorded, but if you want to meet and talk about anything during the time that we have our class, I'm more than open to doing that. I just figured I'd post the lectures so that in the event that you're traveling or something, you could, have that in advance. Other than that, thank you guys so much for coming to class, and I will